Thanks. Chuck Manski from Northwestern Economics. Thinking about coming here, this is, I've dealt, I think most of us have probably dealt, outside of our own disciplines before, and this is a very broad group, and I only know a few of you here, actually. And I know from experience that sometimes there are language differences. I don't mean French versus English. I mean different technical languages, sometimes describing the same things, sometimes with fundamental conceptual differences. Sometimes we're not sure. And so what I want to do, I'm from economics, from econometrics mainly. And what I'm going to use for my own talk, what we call economist rules, which is you can interrupt me at any time. And economists typically interrupt each other within 30 seconds of beginning. But I will shut it off, so it's mostly for clarifying questions and so on, because we just may be using different terms to say the same thing, and you don't want to wait until the end of the morning to clarify that, okay? So that's the way I'll do this. So I have here in the title three terms: identification problems, which is econometrics term, statistical imprecision, everybody should understand, and medical decisions under ambiguity. And just to say up front, ambiguity to me, ambiguity is in the Ellsberg sense, that there's an objective probability distribution that you would like to know, but you don't know everything about it. So in the original Ellsberg-Urn experiment, you didn't know anything. You had complete ignorance of the composition of this urn, or this probability distribution. And in the kind of work that I do, you usually have partial knowledge of it, so you'll be able to confine it to a set of distributions. And that will come from the particular applied context. Now, in working on decision analysis, things can be sort of sterile, at least for me, if you talk too abstractly. And so what I've decided to do is to focus on a particular area in which I've been doing applied work, which is on medical decision making, for two reasons. First of all, medical decision making is extremely important, and everyone's familiar with it. And I mean, and not just medical, but actually public health in addition. So it's important, and so you can see why this is, you might want to study this. It also helps just to make things concrete, so to get ideas straight. So that's what I'm going to be doing. But first, a little bit of background on my on the research program, which has now been going on for about 25 years and has morphed through various stages. So let me begin with something standard in economics, which is the idea of a social planning, of a social planner that wants to optimize social welfare, choose a policy that is best for society. And there's a very standard formulation that goes back to Jeremy Bentham in the early 1800s of maximizing a social welfare function and choosing the optimal policy. Now, the issue, let's leave aside the, at least for now, the practicality of social planning and political environments. I don't want to get into a game theoretic discussion, so we'll take that as an idealization. But even if you accept that idealization of social planning, there's an issue that solving the optimization problem that's set up requires assuming that you have all kinds of knowledge, which you may not have in practice. So there's an example that's been that I find very salient. In economics, there's a kind of a modern literature on social planning along the Bentham lines. A very important development was in 1971, James Murley's on his work on optimal income tax policy. And Murley's, for those of you who aren't familiar with it, he set out a problem of a society that has to choose a tax structure, income tax structure, and you want to maximize the utilitarian social welfare function. And then you solve, here's a mathematical problem to solve, is what's the optimal tax structure, which is a hard mathematical problem because of behavioral responses. Is if I, the critical issue is that if I change the tax policy, then people's labor supply is going to change, okay? So in order to solve the optimization problem, Murley's a theorist. He wasn't doing empirical work, but he was very cognizant that in order to solve the optimization problem, the planner would have to know the labor supply response of the population, right? Not only that, in order to figure out that we get the right utilitarian social welfare function, you actually have to know the distribution of preferences for work and leisure versus consumption. And that's actually requiring an awful lot. So Murley said, let's imagine, he's the theorist, he can do this, let's imagine that we know the distribution of preferences in the population for getting leisure and for consumption, and then we can derive how people will choose to spend their time working versus leisure under any tax policy, and then we can crank out the optimal income tax policy and do redistribution and the things that people like to do. But where are we going to get that knowledge? Okay, I'm an econometrician. I see hundreds and hundreds of papers over the time, maybe thousands of people in public economics and labor economics studying labor supply and how labor supply is affected by tax policy. And even after 50, 60 years of empirical research on this topic, there's no consensus. Okay, so in practice, you can't solve the Murley's problem. There's unknowns. Okay. And so that's a problem of decision. And then it's a question of what structure you put on the unknowns. You could be Bayesian about it and do a standard expected utility thing, but maybe you don't feel comfortable doing that. Maybe you don't know very much about the distribution of preferences in the population, and so you would be doing optimal tax policy under ambiguity. Now, I would love to be able to present a paper on that topic. I'm not, because that's very, very hard, okay? I mean, the math of doing Murley's optimization was hard, and doing this under ambiguity would be much, much harder. And no one has done this, okay? There's been no work on that. So I'm going to look at problems of that type, but that have a simpler structure than the Murley's problem. Okay, now why is it that we may not have complete information? The kind of simplest reason, to me, is that I think everyone's aware of is statistical imprecision. The data that we may have on, say, on labor supply, or I'm going to talk about medicine, on, say, treatment response, be data from randomized experiments or observational studies of treatment response, we'll have finite samples, maybe random samples from population, and so we have to do standard statistical inference from a sample to a population, okay? So, you know, we have 100 years or 200 years, depending on how you want to count a statistical theory on how to do that, and there are more or less sensible ways to do it from a decision analytic perspective, but let's just take that as people understand that. The deeper problems, I think, are identification problems, and for those of you who aren't just familiar with the term, but actually identification problems, which has been the basis of what econometrics has been about since the 1930s, has been about studying the inferential problems that do not go away as sample size increases. The problems that even if you could sample everyone in the population, it's just the nature of what's observable and what's unobservable, is that there's some things you can learn and other things you can't. The problems that don't go away as n goes to infinity are identification problems. Okay, so this is what I spend most of my career studying, is the particular structure of identification problems in different contexts. Now, just to mention one, which is probably maybe the simplest and also maybe the most fundamental, that certainly these days every empirical social scientist recognizes, is what's sometimes called the selection problem, and it's basically the problem of lack of unobservability of counterfactuals. And so the issue is, think about it in medical treatment, is you can get data on a study population, and let's say there are two treatments, treatment A and treatment B. And in the study population, some people receive treatment A and some people receive treatment B. Now, to actually do an analysis of treatment response, for the people who actually receive treatment A, you can observe what happened to them with treatment A. That's, you know, I mean, there could be measurement problems and so on, but let's abstract from them. In principle, you could observe what happens under treatment A to people who actually receive it, but just as a matter of logic, you cannot observe the counterfactual. What would have happened to people who received treatment A if they had received treatment B instead? And to do medical decision making, you want to know that. You want to know what's often called the potential outcome of a person under each treatment. And you can only observe the outcome under one treatment and not under the other treatments they don't receive. So it's an inherent observability problem. It doesn't matter whether your sample size is 1,000 or 10,000 or 10 billion. It's the same issue. For every person in the study population, you get to observe only one outcome and not the other potential or latent outcomes. Okay? So what we want to do formally is to actually to inform medical decision making is to learn the probability of distribution of treatment response across the population. Typically, we're assuming there's heterogeneity in how people respond to treatments. And you can, now you formally get to the math of this, is that you can only learn a piece of that probability distribution. And so there'll be multiple distributions, a set of distributions that are consistent with the available data, okay? So those are the kind of things that I've been studying. What people tend to do is they tend to take the data that's available and make assumptions that are strong enough that you can identify the full distribution of treatment response. That's kind of long-standing approach, not just by economists, but by medical researchers, by basically everyone. I rebelled against that way back in the late 1980s, early 90s, and said, where do these assumptions come from? I got very worried about the credibility of the assumptions that were being made. Particularly, of course, there's the credibility of assumptions that are used in observational studies. But then people say, well, run randomized experiments and that will solve it. But randomized experiments are wonderful if you can do an idealized randomized experiment. But anyone who actually tries to do a randomized experiment knows there are all kinds of practical problems in randomized experiments too, like who actually volunteers to participate in a randomized clinical trial, say, in medicine, and then compliance with treatments, attrition from the trial, measurement of surrogate outcomes, and on and on and on. I could, spend an hour talking about all the problems in randomized experiments in practice, and all of those problems in randomized experiments generate their own identification problems, okay? So I began work around 1990 saying, well, what can we learn under weak, credible assumptions? And typically you cannot pin down the distribution of treatment response fully, but you do have some information. You're not totally ignorant because you do have the data from the study population. There may be some assumptions you feel comfortable making. And typically, mathematically, what I get is that you can make inference that the true distribution of treatment response lies in some set of distributions, okay? And so I did lots of work like that during the 1990s. And and there's an exposition of this. There's like, so many papers, and I've actually written several books. But the place to start, this is what I use for graduate econometrics teaching. This book, Identification for Prediction and Decision. That's probably the best place, to get into this literature. Okay, now what's the connection with decision making? So if you now think about a social planner, and you would like to think about a medical planner, for example. It could be a medical clinician treating patients in the office, or it could be a public health planner, and you're trying to choose the best policy or the best treatment. But you don't know the distribution of treatment response. You only have partial knowledge of it. But by the way, the term that we use is partial identification, okay? So we'd like to identify the distribution of treatment response, but we can't pin it down, so we can partially identify it, so we can confine it into a set of probability distributions. So this immediately, I think, puts the work I'm doing, in the same room as what I think most of you are coming from here, is situations where you don't have full probability distributions. The things you may have partial probability distributions. Again, on language, I used to go to these conferences, of the imprecise probability conferences, and so they'll use the terms imprecise probability, and that's fine. And that's and I'm using it as imprecise objective rather than subjective probability distributions to make a distinction that may matter to some of you. That's fine. I use the term ambiguity. And other terms that may be used, the macroeconomists use the term Knightian uncertainty, which goes back to 1920, because of course they want to attribute to a macroeconomist, to Frank Knight. Some physical scientists I know use the word deep uncertainty. I've seen that with climate change people I come into contact with occasionally who do robust studies of climate change. They talk about deep uncertainty. And for this conference, someone called it severe uncertainty, I think. But I think it all means the same thing, is not having full probability distributions, being able to confine things to a set of distributions. Okay, so around a little more than 15 years ago, I started to move away from the econometric problem of doing inference on these things we'd like to know to what the implications are for decision making. And actually, this paper that's cited here, it's Journal of Econometrics 2000, it actually says that, the title is Identification Problems, whatever, I don't remember the exact title, and Normative Decisions under Ambiguity. So the normative, which is, for this conference is important, is how, if you don't know, if to solve an optimization, let me abstract it for a bit, in order to solve an optimization problem, there's an objective probability distribution you want to know, but you don't know it fully, then you may not be able to solve the optimization problem, okay? And there may be one state, if I can use decision theoretic language of states of nature. There's one state of nature in which the true distribution is this. There's another state of nature in which the true distribution is that. And the optimal policy will be different in these different states of nature. So what are we going to do? We can't solve the optimization problem. So these are basic problems of decisions under ambiguity. Okay, now the question, so then I have to start thinking about decision theory and how to apply it. So I don't have a formal background in decision theory. I've always been around the edges of it. And I have a very pragmatic view of decision theory. So I'll tell you from the beginning, what I'm not going to be doing is axiomatic decision theory, okay? It's not at all, okay? And I guess there's a bunch of philosophers in here and other people like Saki who do this for their, their lives. We could probably spend the entire 3 days arguing about the philosophy of rationality and so on. I don't want to do that. I want to, at least not during my time. Maybe during coffee breaks and maybe after enough wine at dinner we can do that, okay? I'm going to be very pragmatic. And actually, if you want to see my philosophical view, I have an article in Theory and Decision in 2011 with the title Actualist Rationality. That's the title I chose for it. And it's basically an attack on axiomatic decision theory, okay? So let's leave it alone. I'm happy to, these are fun sometimes, those discussions, and we can get into that, but not now. I'm just going to take a very, very simple view of what decision theory is about, is a two-stage decision process. Is that if I have multiple states of nature and I can't solve an optimization problem because I just don't know which state of nature I'm in, and we get different policies or actions that are optimal in different states, then what am I going to do? Well, the first stage, which I've never seen anyone, I think, who disagrees with this, is you eliminate dominated actions, okay? Everyone seems to agree normatively you should eliminate dominated actions. So we try to do that. And in some of the applied problems that I solved, there's actually enough structure that you can actually get somewhere and actually throw away some actions as dominated. There may be some hard math to solve for what's dominated, and sometimes it's easy and sometimes it's hard, but sometimes you can eliminate some dominated actions. Okay, but let's say you've done that, and then you're left with the undominated actions. Undominated actions, of course, is that there's no other action that yields a better outcome in every possible state of nature, okay, either weakly or strongly, okay? So then what are you going to do? Okay, so here's where all the fuss comes in decision theory. And there's the Bayesian approach, of course, which sometimes people view pragmatically and some from an axiomatic perspective. Say, well, just put a subjective probability distribution down on everything that you don't know, and then maximize subjective expected utility, and we're done, and that's the way to do things, okay? And I, as an economist, I grew up with that being basically the dogma. That whenever there's unknowns, you put down subjective distribution and you act as a Bayesian. And it actually requires you to go outside the mainstream to think about ambiguity for applied problems. But I have no philosophical problem with being a Bayesian, but I do worry about the credibility of prior distributions often. Since I do have a very pragmatic view of decision making, anyone knows it's not enough to say there's going to be a Bayesian. I have to say, well, what prior am I going to use? And you can't just make the prior up. You can talk some nonsense about non-informative priors and so on, but anyone who knows study knows there's no such thing as a non-informative prior for 10 reasons that we tell our students, at least I hope. And but if we get into arguments about this, that's okay. Asserting a prior is asserting a form of knowledge. So I've actually, in my own work, gone all the way to the other extreme. Of course, there's a large literature that's on multiple priors, robust Bayes analysis, again, different terms, for this sets of subjective priors and so on. My own work goes all the way to assuming no notion of a subjective probability distribution at all. There's something we're going to know, the truth that an objective distribution lies in a set of distribution, and that's all that we know. Okay, that's the kind of area in which I've done my work. And so the classical approaches for that are typically max-min and minimax regret approaches. And what they both have in common is that they given that you can't weight different states of nature, then one way or another, formally, you try to get something that works uniformly well across all states of nature. And max-min and minimax regret gives you different formalizations. It's very important not to confuse them because they are very separate, to what it means to get something that's uniformly well. Now, what I say here is that there is no optimal way to choose among undominated alternatives. There are only various reasonable ways. The term reasonable is, you know, I use that term all the time, but it's easier for me to quote someone who's used it before. It's not that they can define it any better than I can, but at least they've written about it a long time ago, and they're very famous. So Abraham Wald, in his seminal book on statistical decision theory in 1950, he focused on, I'll say maximin because I want to maximize something. Wald talked about minimax because he was minimizing loss rather than maximizing welfare. And this is a quote from Wald in 1950, "A minimax solution seems in general to be a reasonable solution of the decision problem when an a priori distribution it's on the sigma algebra does not exist or is unknown to the experimenter." Okay, so he says if you're not prepared to put a subjective distribution down, a minimax thing seems reasonable. Now, Wald is a very rigorous mathematician, but he never defined what reasonable meant. Okay, he just left it. This is Wald at the beginning, page 18 of his statistical decision theory book. A more fleshed out thing is from Ferguson's monograph on statistical decision theory in 1967, and I really like, and Ferguson I think just nails it. He says it's a natural reaction to search for a best decision rule, a rule that has the smallest risk no matter what the true state of nature. Unfortunately, and he puts this in italics, the italics in what he wrote, situations in which a best decision rule exists are rare and uninteresting. For each fixed state of nature, there may be a best action for the statistician to take. However, the best action will differ in general for different states of nature so that no one action can be presumed best overall. And then a paragraph or so later, Ferguson says, I love this, "A reasonable rule is one that is better than just guessing." Now, of course, he doesn't define what just guessing means either, actually, but still, you know, it's kind of a low bar for what's reasonable. It says you can look at a variety of things, and the reason I want to spend just a bit of time on this, I think, in terms of those who, you know, view this philosophically and so on, I really want to take the position there's no one right way to deal with ambiguity. And you really need to be more eclectic about this. Now, I've tended to, I focused on maximin and minimax regret, mainly minimax regret, because I like the way it works in practice, okay? Now, just to say, I know there's a long-standing axiomatic argument against minimax regret, dating from Chernoff in 1954. Some of you may know that. I think Chernoff was a very smart guy, but I think he was wrong-headed on this, and we can discuss that later. I set up the minimax regret criteria. I crank out what it gives me. I sort of look at the solutions. They say, do they look reasonable, sensible? You know, would I actually use this in practice? And in the various problems that I've studied, they do seem to. And so I've continued doing that. And so the mathematical work I do is a lot of applications of the minimax regret criteria. Okay, now we can have different views on this. I know there are different ways that people deal with these problems in this audience, but I'm just trying to give you a sense of where I'm coming from. Okay? Oh, and then, so that's for like regular decision theoretic problems. And then if you have also sampling, and that's focusing on the identification problems. If you also have sampling and precision, then you have to deal with the finite sample versions of that, and I apply Wald's statistical decision theory. Wald's statistical decision theory was absolutely beautiful, and for those of you who know it, developed in the 1940s, it was very prominent in the 50s and early 60s, and for reasons that I think are absolutely wrong, it fell out of favor. And it stopped being used, and it stopped being taught by statisticians and by econometricians. And there's only, I can sort of count on, you know, less than 2 hands the number of people I know who actually use Wald's statistical decision theory in practice these days. But I began doing it in the early 2000s, beginning in an article in Econometrica in 2004, and I and some students of mine and some others have been trying to bring it back in, okay? So there's only one place in this talk where I'll mention a bit about that if I get to it. Okay, so that's kind of long background. Okay, now let me go the rest of the time to medical decision making. And so what I talked about up to now could be applied to almost anything. And I have done some work even on macroeconomic policies, of choice of fiscal policy by a government under ambiguity. I have one published paper on that, and there are various, I've used it for criminal justice policy, policing, and so on. But so I want to focus on the aspect of my work where I've spent the most time and I sort of get the most excited about, which is medical decision making. So I've written a series of papers which are listed here. The topics that I've studied on the public health side range from choosing a vaccination policy under ambiguity by a public health agency to drug approval and treatment diversification. And the treatment diversification I'm going to talk about today. And then there's those are public health problems. That's like the Murley's social planning problem. And then there's a kind of much more micro thing of an individual clinician or physician in the office who's treating a particular patient. And how do you do that? So there's the whole literature, for those who are familiar with so-called personalized medicine, and which is very important in practice for us as patients as well as researchers, and is also kind of fascinating intellectually. So I've done some work on that. So here's a bunch of things. Okay, now what I'm going to do in the rest of my time is try to go through some of this work. Okay, and it's very I got to give you enough of a flavor for it that this is meaningful, but of course I can't go into enough depth to really get into it. So I've got like 4 topics here, and I'm probably not going to get through all 4, but I'm going to just try to give you, something on them, and of course there's material to read. Okay, so the very earliest diversified treatment under ambiguity. This is actually the title of a paper in 2009 in the Economics Journal, International Economic Review. Okay, so let me start off with a very simple example that I've used in teaching. Philosophers would call this a moral dilemma, okay? But I'm going to just view this as a decision theoretic problem, just to illustrate things, and then the math is going to abstract from this very simple moral dilemma. Okay, so I make up a story where there's a new disease which I call X-pox, like smallpox or something, that's sweeping a community, and I just make up the story. So it's going to be tough to deal with this. You can't avoid infection. If you're untreated, you're going to die, period. Okay? Now, you have 2 teams of medical researchers, and they propose 2 different treatments for this X-pox, and treatment A and treatment B. And there are 2 states of nature. There's one state of nature in which treatment A works and treatment B doesn't, and the other in which treatment B works and treatment A doesn't. Those are the only, you know that, so that's actually knowing quite a lot. The problem is you don't know which treatment works and which one doesn't. Okay, so let me make the problem tougher. You might say, well, let's run a randomized clinical trial. And say, no, there's no time for that, because everyone's going to die within 2 weeks or something. So there's no time to run a randomized trial. You say, well, let's give everyone both treatments. And I'll say, no, you can't do that because there are side effects. If you give someone both treatment A and treatment B, they die for sure. So you got to decide what to do. Okay, so that's the moral dilemma. Okay, now let's imagine there's a public health agency, and I want to maximize the survival rate, overall survival rate in the population. So social welfare is linear in the survival rate. If I view this from the Bayesian perspective, it's very simple. I have a subjective probability that treatment A is the one who works and treatment B is, and I put, this is a risk-neutral social planner, the way I've set it up. What you'll do is you'll give everyone, everyone treatment A if treatment A has the higher subjective probability of being the one that works, and otherwise everyone's treatment B. So it's going to be all or nothing if you're Bayesian. If you view this from the maximin or the minimax regret perspective, this is with only 2 states of nature, this is a very simple case where maximin and minimax regret actually give you the same solution, even though in general they don't. And the solution is the one that you might just imagine, as being sensible even without setting up a formal criterion, which is to give half the population each treatment. And if you give half the population each treatment, it's very easy to see from the maximum perspective, the cup is going to be exactly half full, half's going to survive, half's going to die. Now, I would think to me, that's a reasonable solution. I do not want to call it an optimal solution. We could argue philosophically forever about whether it's better to do that or to take the chance with the Bayesian thing that either everyone survives or no one survives. But it would certainly want to contemplate that's a reasonable solution. Now, I have a note here that what's really going on here is a property of minimax regret, not maximin. because the formal result that I will prove, and I'll give you in a moment, is that minimax regret always diversifies in a broad class of situations like this. With max and min, it was very special to having two states of nature. Max and min, if I just add a third state of nature in which neither treatment works, then max and min is useless. Everything is max and min in that case. But minimax regret will still give you the half-half allocation. And that's the kind of like practically working out things. What does max and min give you? What does minimax regret give you? And I find minimax regret seems to give kind of appealing solutions. Okay, so the term I use here is it diversifies. Okay, you diversify treatment by giving this 50-50 allocation. By the way, this is not a mixed strategy in game theory. It's not that with some probability everyone's going to get one and some probability everyone's going to get the other. It's a deterministic strategy that exactly half the population gets one and half that gets the other. What is random is, of course, which 50% of people get. You got to choose at random who gets treatment A and who gets treatment B. But half the population gets one and half that gets the other. And this shows a very big difference between viewing this as a micro problem for an individual person versus a macro problem for society, because an individual cannot diversify. I either get treatment A or treatment B. I either live or die. There's no way I can insure myself against this. But society as a whole, from a public health perspective, can ensure by diversifying treatment in this way. Okay? So that's the XPOX example. Now, why is diversification interesting? It's because it prevents gross errors from occurring. Everyone's familiar with diversification in finance, for having portfolio diversification of financial assets. And the reason for diversification is exactly uncertainty about asset returns. Now, the standard finance literature on diversification comes from expected utility theory, of course, where instead of assuming risk neutrality, you assume risk aversion, that people have concave transformation of money as the utility function. And with enough concavity, then you get diversification out of expected utility. What I'm saying here is you don't have to have expected utility theory to get diversification. You can get diversification out of minimax. And I think lots of people who work in decision theory under ambiguity have found that as a characteristic of minimax. And I'm not going to claim that in 2009, when I found it in my context, that was the first time. I don't know how far back demonstrations of diversification go. They're in some of the axioms that you would use, right? I think so. This is an old idea, but I think it's quite important. So the notion of diversification does not have to rest on expected utility theory. Okay, now this is the algebraic version of what I was just talking about. So now there are two treatments, A and B, and now to formalize things, we have a population of, imagine this is a population of patients, or keep the XPOX example in your mind if you want, but let me think about it more broadly now. There's a treatment response function, for each person, small j, there's a yj dot maps treatments into outcomes. Heterogeneity in treatment response is very important in general. The old literature in medicine would assume everyone would respond to treatment in the same way. Lots of applied economics work does that. But I think that's really out. I mean, there's lots of sensitivity to heterogeneity of treatment response among all the applied people I come into contact with. So let's allow photal heterogeneity. Everyone may respond to treatments in different ways. What we would like to know is P of y dot, that's the population distribution of treatment response. This is the objective probability distribution that I was alluding to before. I'd like to know is what's the distribution of response to each treatment within the population. If I can set that up, if I know that, then I can solve an optimization problem as a problem of decision making under risk. Okay, if I have that objective probability distribution, I have a classical problem of decision making under a risk. Just for technical reasons, as economists often like to do, we assume a large population, atomless populations, probability 0 for each person. It just gets rid of a lot of technical issues dealing with finite or countable populations. Okay, and to make this simple, for here, let's assume people are observationally indistinguishable. So there are no observed covariates. Obviously, there will be observed covariates. You're treating males and females, young people and old people, but we can condition all that and just look within a group. Okay. So what's the decision now for the social planner is to pick a value of delta which is in the 0-1 interval, is to assign a fraction delta of the population to treatment B and the remaining 1 minus delta to treatment A. Okay? That's the very practical decision problem. Now, let's assume that the planner wants to maximize mean welfare. So this is a utilitarian social welfare function. Okay? And this is the generalization of the X-box case with the survival rate. So for each person, there'll be a UJT, is what's the contribution to social welfare if person J gets assigned to particular treatment T. And then we have two extreme cases. Let's say you assign everyone to treatment A. Then social welfare, if everyone gets assigned to treatment A, is the expected value of UA. And I'll just call that alpha for short. And if you assign everyone to treatment B, then you'll get social welfare beta. Now, if we do an allocation, a delta, that's in between, given that it's going to be random who gets A and who gets B because they're observationally identical, then here's our social welfare function. The social welfare of assigning a fraction delta to treatment B and 1 minus delta to treatment A is beta times delta plus alpha times 1 minus delta. Okay? And you can rewrite that, of course, as alpha plus beta minus alpha delta. And now we can immediately see where you can optimize and when ambiguity arises. The whole question is, I don't have to know beta and alpha exactly, but do I know the sign of beta minus alpha? If I know the sign of beta minus alpha, I know it's optimal to put everyone in treatment B or treatment A, depending on whether that sign's positive or negative. To put this in very standard applied language, beta minus alpha is the average treatment effect, the population-wide average treatment effect. Anyone who studies medical decision-making or lots of microeconomic decision-making knows the focus on average treatment effect. You say, well, why is the global population average treatment effect important, particularly the sign? Because if that's positive, then one treatment's better for everyone, and negative, it's the other, okay? So if I know the sign of beta minus alpha, if I have enough information to do that, then I solve the optimization problem. It's a standard problem decision under risk. But let's say I don't know that. Let's say I know that alpha beta lies in some set, alpha S beta S, S element to capital S. So capital S is the state space, or what a statistician or econometrician would call the parameter space. It's just other language. So this is what I know. Now, I'm going to keep this abstract, but how do I know this set? That's where all the econometric, all the work on identification comes in. Because exactly what I can learn about alpha and beta depends on the nature of the data that I have, whether it's observational or randomized trial data. It depends on what assumptions I make. I just learn that alpha and beta lie in some set, okay? And then I face ambiguity if remember what Ferguson said. If there's a state of nature in which alpha is bigger than beta and another state of nature in which alpha is less than beta, then you just can't say what's optimal, in that quote from Ferguson. And so then I face a situation of ambiguity, okay? So that's it's a simple problem. It's a static problem with two treatments, but it really captures an awful lot of what's in the literature. Okay, now let me just go on technically. Let's assume this state of possibilities is bounded. We have a minimum value of alpha, a minimum value of beta, maximum of alpha, a maximum of beta, and set up the criteria of maximization of expected welfare and maximin. Let me do that very briefly, and then I'll come to min-max regret. So what's going to happen, this is a risk-neutral social planner. If you're Bayesian about it, then all you care about is my subjective mean for alpha and beta. And I put everyone in treatment A if the subjective mean for alpha is bigger than the subjective mean for beta, and vice versa. So I get the corner solution that you get under risk neutrality if you're a Bayesian. And this is the generalization of the X-box case. Maximin is this, of course. This is just the statement of what the maximum criteria is here, is that for any given action delta, then I'm going to find out what's the worst welfare I can get if I choose delta. So I minimize my social welfare across all states of nature here. And then I choose the least bad action, which is the max over the min here, and that's maximin. Now, what happens as the result? It depends on this topology of capital S, the state space. In the X-box case, where the only possible states of nature were 0, 1, and 1, 0. Either one works or the other one doesn't, or vice versa. Then the solution to maximin is the half-half. In general, that's not the case. In particular, if you had a rectangular set, that, let's say, the alpha can range between alpha L and alpha U, and beta from beta L to beta U, and anything in that Cartesian product is possible, or actually weaker, just let these two things both be possible, the minimum, then the solution is a corner solution for maximin. So this is just saying that in general, maximum is not going to diversify. It will in some special case, like in Xbox, but it will not in general. Okay, minimax regret. So here's the result. This is a very simple result to prove, and it actually there's a version of it even in my textbook in 2007, but mainly in this 2009 paper. You set up the minimax regret criterion. The outside is the minimum over the different actions. It's the different fractions of people to allocate each. Well, let me start in the middle. This is regret. I'm assuming some people know what these things are, and maybe some people just aren't familiar, so I have to take it a little bit. So regret is this. Regret is, by definition, is you take a particular state of nature and a particular action, compute what's optimal. If I knew the true state of nature, then I would do the thing that's optimal, and I would get the maximum of alpha s and beta s. But if I pick some delta, some fraction, you know, and that, I would pick delta to be either 0 or 1, depending on whether alpha is higher than beta. If I choose this thing, I get this. Regret is the optimum minus what I actually get with delta. So of course, that's just what Savage called, well, he didn't actually use the term regret back in 1951 when he defined this, but that's what regret is. And I don't know what regret is, of course, in practice, because I don't know the true state of nature, but I can compute maximum regret, which is here, across all states of nature. That's the uniformity that I referred to before. And then I want to choose the action that minimizes maximum regret. So this is the math. And the solution, well, there's a bunch of symbols I won't go through. But it turns out the solution is always diversification. This MB, which is defined up here, and the MA, these are all positive numbers. That's all you need to know. And the solution is MB over MA plus MB. That's the abstract solution. In the case, and that's always interior to 0, 1. So minimax regret always diversifies, in this case, always, with 2 treatments. Okay? In the case where you have a rectangular set of state space, then this simplifies that this is the first. So this is a very practical numerical solution, that the fraction you would allocate, it's not just saying you diversify in general, it gives you a very specific fraction of people to put into treatment A versus treatment B. And this is that fraction, the upper bound on beta minus the lower bound on alpha, divided by that, which is here, plus the contrary, the upper bound on alpha minus the lower bound on beta. So depending on what information you have, the particular structure of what we call the identification region of this set of possible distributions, you get a very specific. So this becomes very practical for medical or public health decision making. It's not just saying it abstractly you should diversify. You should diversify with this fraction of people put into treatment A versus treatment B if you're in this informational situation. Okay? Okay, then I go on, and just for lack of time, just very briefly, I do that was a static problem, and then I do a multiple time period version of the problem. And the interesting thing then is now I have a sequence of cohorts of patients. And what happens now that's new, of course, is I can learn. Is that I can treat, let's say I'm in the first time period, and I allocate 70% of people to treatment A and 30% to treatment B, but then I can see the outcomes of that. I'm actually running randomized experiments. The diversification that's achieved by minimax regret, it actually has a side benefit that you're doing it to diversify, but as a side benefit, you're running a classical randomized trial, and I can learn from that, and then reduce my uncertainty in treatment 1, 2, 3, 4. I narrow the state space, okay? So I can only take a second to talk about this. I have a whole line of work which begins here, but it's in other papers as well, when I think about learning, not in Bayesian terms as updating from a prior to posterior, but learning as sequential reduction in a state space, okay? So that you get, as time goes on, you get more information, the state space shrinks. And this is a particular way that can manifest itself. I have other papers that even earlier ones than this actually, that manifest that sequential reduction in a state space as learning under ambiguity as well. So anyway, I call this adaptive diversification. And there are different ways to implement it. You can do it by the static minimax regret criteria. Let me just skip over this because I do want, and you can even then apply this possibly to drug approval, but I won't take the time to do that because I at least want to talk a bit, because in terms of the small amount of time I have, about at least the second problem, which is the one I've been working on most recently, which is on personalized medicine. Okay, so I don't have, again, enough time to go through this in detail, but let me let me lay out the problem, which I think is quite fascinating and very, very practical in medicine, is that we have this whole movement, both in the United States and in Europe, towards personalized medicine, which means in practice that we want to condition treatment choices for patients on as many covariates as possible. The doctors know a lot about each patient. There can be, diagnostic tests, medical histories, genetic tests, and so on. And we like to condition treatment on as much as possible. Okay, here's the issue. We have all this stuff in medicine about so-called evidence-based medicine, which is, the wonders of randomized trials and so on. The problem is if you go read the literature on evidence-based medicine, the use of randomized trials, and see what does it actually tell you about prediction of treatment response, typically they'll only condition on a few covariates. You'll learn what the distribution of treatment response is among older men or younger women, among blacks or whites, or so on. But then the doctor, patients come into the office, and they actually know a lot more, but there's no evidence out there. Okay. So what goes on is you'll have what are called actuarial prediction tools. These are regressions. What used to be called regressions and are now called machine learning. That's another terminological. There's no distinction at all between a regression and machine learning. Okay, but I think some people appreciate that comment. I think. So this go back, where you just predict treatment response given on given the data that you have, and you do a firm prediction, but based only on a few covariates. But doctors don't like that because it means that they shouldn't use all this other information they have. So what do doctors do? They use what's called clinical judgment. And what clinical judgment means is they try to use all the other information that they have about the patient, and the way they do it, informally, the way they do it is by being Bayesian. So if you actually look at what clinical judgment means, if you see a definition, it means that you subjectively form a probability of treatment response, distribution of treatment response, conditional on everything you observe. Okay, now the kind of beautiful thing is, and I could take 2 hours on this, so I know I'm not going to be able to, is that there's a psychology literature that dates back to the 1940s and 50s that compares in practice how well do doctors do, and not just doctors, you could do the same thing with admissions officers at universities and so on, using clinical judgment, there's conditioning on lots of covariates, but not knowing exactly how to do it, versus the actuarial prediction. And they very consistently find that the actuarial prediction does better in terms of predictive accuracy. This is a psychological result. I tend to be skeptical about empirical research, but it does seem to be quite a strong result. And so what the psychologists say is the doctor should not use clinical judgment. They should just use the actuarial prediction or the machine learning or whatever. Doctors don't like that. My new paper on this, which I don't have time to get into at all, because I could explain exactly what the identification problem is that underlies this, is you should be able to do better. You should be able to use clinical judgment, but doing it totally subjectively in your head is really asking an awful lot of doctors. It turns out there's some math of the relationship between what we call the short conditional distributions, predicting treatment response, conditioning on a few covariates, versus what we call the long distributions, conditioning on a lot, and you can do the math that sets that out. That is what's called the ecological inference problem from the sociology and political science literature dating back from 1950. If I had more time, I'd explain it, but if you ask me a question, I'll explain it. And then I sort of crank out what this is, and then I talk about decision-making in this context. So it's a very different context than the one I described before, but fine. Okay, and just take 1 minute. That's all I'm going to say about that. I'll just take one further minute just to say, go through all these slides. Another very recent paper is on choosing sample size for randomized clinical trials. This is in the Proceedings of the National Academy of Sciences. The typical way that sample size is chosen for randomized trials is by statistical power calculations for doing hypotheses tests. From a decision theoretic perspective, this makes about minus, I would say 0 sense. I'm going to say about minus something sense to do statistical power calculations. It's a very entrenched institutional norm. If you approach choice of sample size in a randomized trial from a formal walled type statistical decision-making perspective, you get very different looking results. This paper in PNAS with Alex Tetenoff, who's at Bristol, that's what we do, and you can read the paper, but I'm basically out of time. Okay, so I will stop here at least a couple of minutes for discussion. No one used the economist rules to interrupt me. Okay.
So in your XPOX example, I can't see why you think it's reasonable to have a utility function that's linear in the proportion of people surviving. It means that if I have a strategy in which there's a 50% probability that everybody survives and a 50% probability that the human race is wiped out, this is equivalent to a strategy in which 50% of the people are guaranteed to survive. I don't think that makes sense. I think your reason for rejecting the Bayesian approach is simply that it does that. It gives you a chance of wiping out the entire population. And of course, you wouldn't do that because the utility isn't linear.
Well, okay, so we can argue about what the social welfare function for the social planner should be. And of course, it is the case that if you assume that survival is a concave function and sufficiently concave, then you will get diversification. You won't particularly get 50-50. You'll get something else depending on exactly what you assume, and that would be fine in that context. However, I don't want to take a stand. I said this is just an example to make a point. In general, out of expected utility, even with concavity, you don't always get diversification. You will get diversification with the expected utility theory with sufficient concavity in the utility function and sufficient spread in the subjective probability distribution. You can still get corner solutions in subjective expected utility theory. It's not that risk neutrality is just a weird case that stands on its own. So there'll be cases where you do get diversification, cases where you don't. What social welfare function is the right one? I don't know. You know, economists typically take the view that this is, in terms of individual utility maximization, that if you want to be risk neutral or risk averse, it's a personal decision. And that is not right or wrong to be risk averse versus risk neutral or risk loving, that it's just a personal decision. So that's the way I want to view that. And I don't want to say there's a right social welfare function. This was just for and by the way, in my paper, there is a section with nonlinear welfare functions, and I do go through some of this. But the linear case is the starkest case. Yeah. Yeah.
Thank you for a great presentation. 2 quick follow-ups. I was curious about the subjective judgment of the clinician looking one-on-one with a patient and that failing compared to empirical actuarial estimates of risk. It seems like a lot of cases really might have fairly deep uncertainty about what the diagnosis is. So I'd be curious to hear how you see the subjective playing out if you can't even put it into a reasonableness framework. And then the second thing would be, how do you see some of the things you've played out in terms of expert panels for medicine, like the FDA?
Okay, now I haven't done expert panel work at all. I think it's, for the FDA. Well, yeah, I wish I could sit in on the FDA panels to see how they actually do this. I haven't actually do that. I actually, totally separate type of my work, I do lots of elicitation of subjective probability distributions, totally Bayesian, from ordinary people, from households. I don't, in my own work, haven't done it with experts, so I don't really have anything to say. I know people who do, but I know there's going to be talks on that, so I'm being interested to hear them. In terms of the first question, the kind of example is, I hope this answers it, I work through some very specific examples in this paper, and one I do is on prediction of breast cancer, and there's an actuarial tool, the National Cancer Institute website, where you can just go online and a woman can put in 8 attributes and get a predicted probability of breast cancer, an exact, your probability is 0.19 or 0.08 or something like that, conditioning those attributes. But when a woman goes to the gynecologist, there's actually a lot more that the gynecologist will know about that woman that isn't used in this prediction tool that's used. And the mathematical thing that I get into is that if you want to predict based on the longer set of covariates, the other things that the clinician knows, like in this case whether the woman drinks a lot of alcohol and things like that, then you might be able to put a credible bound on that probability of getting breast cancer. And then the specific question of decision-making under ambiguity is if I can put a bound on her risk of breast cancer. And the treatment question now is I just do screening or do I do prophylactic treatment? You know, prophylactic treatment may be drugs or even prophylactic mastectomies and things like that are done. Then, and if I only get a bound on the probability of getting breast cancer, then I actually crank out a minimax regret solution to that. That's in the paper. I didn't have time to do it. So that's how I would approach that kind of problem. And that's what I hope to, you know, get engaged with actual clinicians to see if they might actually do that. Yeah. Okay.
Thank you very much.